Okay, the next part where we are going is what is called periodicity. And periodicity has to do with certain trends in the periodic table. So I showed you one trend in there, and the one trend was just the S block and the P block and how to fill electrons out. The other trend has to do with how the atomic size changes in there. Okay, and there are some other things that we have to talk about. But I need to keep in mind that when I talk about these periodic trends, that we are not talking about the transition metals. Okay, in this one, transition metals are a little bit different, and now you understand why they are different. Okay, because when the electrons are filling in the transition metals, they're going into the core. They're not going into the valence shell. So the effect is not the same, okay, as it would be for the main group elements, because in the main group you're filling out the valence shell. Okay, so the effect is quite different. So we don't count for transition metals in whatever we are going to do now. And that is, of course, periodicity. So the first concept I need to explain to you is what's called effective nuclear charge. And if you understand effective nuclear charge, everything else is just a piece of cake and not very hard. Effective nuclear charge, I think, is written as ZEFF. Okay. And what effective nuclear charge really is, here you have two things to look at. One is the nuclear, one is the charge. The nuclear means that something is coming from the nucleus. Okay, you have, and the charge is coming from the electrons. So here we have electrons in the various shells. When you're filling out helium, you filled out only one shell. When you filled up to neon, you are into the second shell. When you are in argon, you are in the third shell, okay, and so on. So your shell numbers are increasing. So which means that you can have electrons here and here, okay, as well. So here, let's say you have a maximum of 2 electrons. Here you have a maximum of 8 electrons. So between the nucleus and the electron, there is going to be some attractive forces. Why? Because the nucleus has the protons. Okay, and so therefore if you have positive here and negative here, it is going to have some attraction, okay, in there. So that is called the effective nuclear charge. Okay, that pull that the nucleus has for the electrons. Remember I was telling you before that these electrons, they're just on a path. There is no highway or anything like that, right? They're just held by forces, just like the earth is around the sun. Okay, there is just a gravitational force. And so the force here that is holding the electrons is actually coming from this nuclear charge, okay, which is the positive force in here. So you have to think about the intensity of that attraction, okay, that the electrons have to the protons. So for example, let's say we have 2 protons and 2 electrons. They will have a different kind of attraction versus if you had 6 electrons here, and now you have a total of 8 protons, right? Now, since we went into the second shell, the attractive forces that these 2 electrons are feeling towards the proton is going to be different than what these 6 electrons are feeling. Am I correct? Yes? Okay. Because these are further away, right? So this shell is closer to the nucleus, so the attraction that these 2 electrons have is way more than what these 6 electrons have, okay? And if you fill out these 8 electrons as well, and then start filling out the third shell, so now we have a total of 12 protons. But the effective nuclear charge has decreased for these 2 electrons, hasn't it? Because these 2 electrons are farther away. So the effective nuclear charge these 12 protons are expressing is primarily for these 2 and then the 8. And so as the shell numbers increase, what happens to the effective nuclear charge? Increases or decreases? Decreases. And that's the most important concept, okay? If you understand that concept, then the next 3 things that we're going to talk about is going to be very easy. Are we good with this? Okay, so it is all about the number of protons and the electrons and where those electrons are. Yeah.
So that's why the outermost shell electrons can bond or go to a different.
But they can be given or taken, so that's a different thing. Yeah. Okay. That has to do. That's not to do with the effective nuclear charge. That's a different principle. Okay. So the three things that we are going to talk about in periodicity is going to be the atomic size, ionization energy, and electron affinity. Let me see if I can do this in the next 10 minutes. I think I can, if the internet opens fast enough. Fluid periodic properties. So here we go. Three things to talk about over here: atomic radii, ionization energy, and then electronic affinity. Okay, and so the first thing over here is the effective nuclear charge, which is what I was just explaining to you. So there are two things that happen. Once I explained to you about the shells as they keep increasing, but the other aspect is if you have the nucleus, and here you have 2 electrons, here you have 1 electron, so 3 protons. Let me turn the light on again. So now if you have, instead of the 1 electron, if you had 2 electrons and 5 electrons here, so now you have 7 protons. The attraction that these 5 electrons are feeling, is that more than this 1 electron or less than that 1 electron? Less. More, because you have 7 protons here. That 1 electron feels only the 3 protons, but here these 5 are feeling 7 protons. Okay, so that's a lot more. Right? So there are 2 kinds of effective nuclear charge that you need to understand. One is going to the new shell. So in the new shell, the effective nuclear charge decreases. Okay, but within the shell, so if you go from 1 electron to 5 electron in the same shell, the effective nuclear charge is going to increase. Okay, so that's the CFF. Okay, that's going to actually increase, and that's what the slide shows over here. Okay, is that if you increase the number of electrons in the same shell, okay, then the effective nuclear charge is going to increase, and if you go down, it should actually decrease. So have your periodic tables in front of you if you could, because again you can write on it and just write your trends. Okay, there I have some nice ones on the PowerPoint, but as you know, I like it if you write it on your own. So here are the 4 trends we'll talk about. The metallic character is a little bit different. Here is the atomic radii. So as you go across a group, the number of electrons are increasing, effective nuclear charge is increasing, attraction to the valence shell is increasing, so which means the electrons are getting pulled inside towards the nucleus, which means that the size of the atom is going to decrease then, okay, as you go towards the right, because as you go across a row, the electrons are entering the same valence electron shell, okay, that's where they're going. But if you go down, if you're going down, then a new shell is being added, which means that the electrons are getting farther away. So if they go farther away, they feel less of that effective nuclear charge. Okay? If they're in the same shell, they feel it a lot more. So you can see that for all of these rows, as you will go to the right, the size is going to decrease. Here also the size is going to decrease. Okay, and so on. Within the transition metals, there is no trend because the electrons that are coming out are the core electrons, okay, or wherever they're going are the core electrons. So core does not affect the size as much, okay, but the valence electrons affects it. So you can look at any row, it's going to be the same thing, and you can look at any column and it's going to be the same thing, which means that the size is going to increase of the atoms as you go down, okay, a group. And that is because the electrons are going into the new shell. And how is that? You know that because as you go from chlorine to bromine, you went from 1 to 3rd shell to the 4th shell. Okay, and so therefore you are adding electrons to a new shell. So that is your atomic radii, And there are some nice charts over here, some graphs. If you want to go over this, this is kind of nice. You start with a large, go small, 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 and boom, a new shell comes in. Then again go small, 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 and then again you add a new shell. So those kind of things. Okay, so that's the atomic radar. Yes.
So as you go down, the effective nuclear charge decreases?
As you go down, it decreases. Yes. Ionization energy is the amount of energy required to remove one electron from an atom in a gas phase. Okay, not from a solid phase, not from a liquid phase, from a gas phase. Okay, so everything is at least in the same, what do you call, physical phase. Okay, and so the amount of energy it will take to remove one electron. So just look at the diagram that we have on the board itself. Okay, so here you have one electron, here you have 5 electrons. These 5 electrons are feeling a lot more of that effective nuclear charge, right? That's what we decided. So then, what is easy to remove? This 1 electron or the 5 electrons? The 1 electron is easy to remove. Okay, even the 1 from these 5 is going to be hard to remove. Okay, and so the 1 electron is easy to remove. 2 gets a little harder, so which means that as you go across the group, across the row, the ionization energy is going to increase. Okay, because you're putting electrons in the same valence shell. So if it's in the same one, the effective nuclear charge is increasing, attraction is increasing, so it's really hard to remove an electron. When you go down, okay, then you're adding a new shell. So now effective nuclear charge is less, and if it is less, it's easy to remove an electron. Okay, so that's what these trends indicate here. Okay, that the ionization energy is increasing this way, and it is decreasing this way. All right, and those are the arrows you need to draw out. Okay, on your periodic tables once you get a little time. Again, there is a chart for this. Okay, right here. So in this case, you start with lithium as being the lower energy, and you go higher, higher, higher to neon. So by the time you get to the group number 8, it's really very hard to remove an electron. And it's just not possible. And you remember, we said that we have anions over here. They gain electrons. They don't give electrons. Okay, they don't form cations. Only cations are formed from the left-hand side. Okay, yeah.
Is that why none of the noble gases will bond with any of the other
That's
gases?
one of the reasons, okay, because they can't give electrons. It's very hard to remove an electron. I'm going to not be able to finish. Let me just bring one more thing to your attention, then I'll finish everything in the next time. And this ionization energy chart, this is very interesting because this one gives you the first ionization energy, second, third, and fourth. It's very interesting, okay, because let me show you what it really means, okay? So if you have this going on, 7 protons, 7 electrons, and then you remove 1 electron from there. So now you have 2 electrons, 4 electrons here, and you still have 7 protons over here. What happened to the effective nuclear charge? Did it increase or decrease? Increase. So then the ionization energy for this electron would be higher or lower than the first one? Higher. Logically, okay? Just keep it logical, and then you will realize that the second ionization energy is higher, and that's what this chart also indicates. Okay, so if you look at some of these numbers here, you will see that the first is lower and the second, look at that, what the difference is between the first and second. Okay, it's because you removed an electron, so the number of protons are still there. Okay, so the effective nuclear charge increases, okay, for that one. Okay. If you want, please go ahead and listen to the rest of the lecture. It's really not that much, okay? And then I will, do a little review for you. This is a nice, chart to have. It has all the trends on there, okay? Along with the size of the arrow, you have to appreciate this. The atomic radii is decreasing as you go to the right, so the arrow is narrowing as you go right. It's kind of a fun chart. So keep that one handy, and we'll finish this off next time. Okay. Radii, ionization energy, right here. This is where we were. And I think I was kind of on this slide last time, isn't it? With the second ionization energy. Okay. Third one. on and so on and so forth. Okay, and so you really have to look at the element before you can decide whether the second or the third or the fourth ionization energy is going to be higher. Usually the questions you get is for ionization energy in general, and when that is the question, it's just about the first one. That's it. Okay, so if there's a question like arrange the following elements in increasing order of ionization energy, then just talking about the first one. Okay, don't get confused about second and third in those cases. Okay, so that was ionization energy, and that is the removal of an electron. Okay, from there. Now the electron affinity. Electron affinity, this is the official definition of it, is the measure of energy released when an electron is added. Okay, and the more energy is released, then the lower energy measurement means that, okay, I'm not going to go there. All right, high energy release measurement means more energy. Okay, I have no idea what that is. Okay, we'll just leave it to the first sentence. Okay, I'll remove the second one. So electron affinity is the measure of energy released when an electron is added to a valence shell, and this increases as you go right. The way I look at electron affinity is exactly what the word says, affinity, which one likes more electrons. So whatever is on the right-hand side of the periodic table, they like electrons more, okay, because they're the ones who are able to accept the electrons more. The ionization energy is opposite of electron affinity. Ionization energy is removal of electrons, whereas electron affinity is giving electrons to an atom. Okay, so they work opposite way. So of course, if, well, energy-wise, okay, and so energy will increase for how much is being released as you go to the right-hand side. When I ask you questions about electron affinity, again, just remember the trend, okay, that's the important part. So again, if you have your periodic tables, go ahead and write that it increases as you go right and decreases as you go down, okay, for electron affinity. Typically, the questions you will get for the periodic trends are atomic radii and ionization energy. Okay, electron affinity is generally not questioned that much. And then metallic character, I think this is not in your textbook, or maybe it is, I'm not sure. But I like to talk about it because it's an important part of the periodic table. Okay, because there is a trend in the periodic table, because as you go towards the right-hand side, what happens to the metallic character? Increases or decreases? As you go to the right of the periodic table?
Decreases.
It decreases because you're getting into the non-metals. And then as you go down, the metallic character increases. Okay, and so that's the trend, okay, in general. So some of the true non-metals are going to be in group number 7 and 8 then. Okay, 8 of course is all noble gases. And then group number 7 is also traditionally all non-metals. And in group number 6 with the oxygen, only the last one, polonium, is the metal. Okay, all the other ones are considered to be non-metals then. So the group number 4 really is the best one, okay, to look at when you're thinking of metallic trends. Because in group number 4, you have the classic non-metal, which is carbon, and then you also have the metalloids, and then you have the two metals at the bottom. Okay, yes?
So you said electron affinity increases as you go down, but it also
No, decreases as you go down.
decreases as you go
Yes.
down.
And increases as you go to the right.
And increases as you go down. Okay. Thank you.
Okay, no problem. And if you miss anything, there's a very beautiful slide coming up. Okay. So metallic character, you told me about all of this in chapter 2, because that's when we were learning about the periodic table. So these are the metallic characters, okay, of any element, that they should be good conductors of heat and electricity and so on and so forth. And then we have the non-metals, and then of course the metalloids, which have a little bit property of both. Okay, so you can use them whichever way you want to use them. There is one additional thing that is in here, okay, that was not there before. Okay, and which is that most of the metals will form basic compounds with oxygen. Okay, and this will come up again as we talk a little bit more about periodicity. Okay, but this was not there before. And for non-metals, it's the acidic. Okay, so they're opposite that way. Okay, and what that really means, if I were to write an equation out for that, for those those of you who were in the lab yesterday, who was it? I can remember only one yesterday. That's it? Somebody was in New York. Okay. All right. So if you take magnesium, which is something that you've done in lab already, okay, and you treat that with oxygen, which is also something that you've done, was the empirical formula lab that you did, and you form magnesium oxide. Okay, so if you were to take this oxide, which is a metallic oxide, and the equation is not balanced, and if you were to add water to this, you would end up getting magnesium hydroxide, okay, from this. That's what that point is, that you actually, if you have oxides of metals, then they will form basic compounds, okay, from there, which means in treatment with water, okay, the water has to be present in order to do that. So this is the kind of thing we're talking about. We did this in lab yesterday with sodium. So if you take sodium, you add that to water, you will get sodium hydroxide, okay, pretty much, that's how you do it. And then for the non-metals, if you were to take, say, sulfur, and again burn that in oxygen, okay, same thing, you're forming oxides, and then you get sulfur trioxide, and you add water to that, you will end up getting acids. And if you look at your lists of acids and bases from chapter 2, you will see that all of the bases, they all have metals in them, and all of the acids all have non-metals in them. Okay, and so this is how they're also made. Okay, so when in industry, when they have to make acid, this is how they will make it. Okay, and so very common thing. But this is a property of metals and non-metals. Okay, so that's the metallic character, and there is a general trend, okay, in there. So here's a trend for you. This is a nice table. In case you haven't downloaded the PowerPoint, again, this took me a little while to make, but I'm very proud of it. I don't know about you guys, but there's everything in here, and starting with effective nuclear charge, and then increase, decrease, it tells you all the trends. Okay, right here gives you a good reason also for everything, so make sure you go through this when you get time. And then there was another chart, right here, this one, okay, which is also very good. The only one that you have not done yet, okay, is electronegativity. But go ahead and print this out and keep it with you, because next chapter we're going to do electronegativity. Okay, so then you'll have everything on one. Okay, and so it has atomic radii and ionic radii we'll talk about in a minute, electron affinity, ionization energy, and so on. So everything is there for you. Okay, now let's talk about the ionic radii. This is an interesting thing because it's not the same as the atomic radii. In atomic radii, everything is neutral. You have your total number of electrons, and you also have the protons in there. But when you start looking at ions, things change a little bit. Lines up, lines down. So for example, if you have magnesium, I don't know why I like magnesium today, but it's fine. And magnesium has 12 protons and 12 electrons. So 2 here, 8 here, and 2 electrons over here. Correct? Okay. So this is what's going on in a neutral atom. But then what happens is when you start having something like magnesium 2+, where you have the nucleus, but in the nucleus you still have the 12 protons, but now you only have this much, right? Because you gave away 2 electrons, okay, in there. So when you look at this and this, okay, the neutral atom and the ion over here, specifically cation over here, what happened to the effective nuclear charge? Did it increase or decrease in the ion? Did it increase or decrease for the ion? Increase, okay? It increased over here because you have 12 protons pulling only on 10 electrons, where it was 12 protons pulling on 12 electrons. Okay, so here the effective nuclear charge has increased. If it is increased, it means that your atom is going to shrink now. Okay, and so that's the trend that you see over here. And when I turn off the lights, you'll see it a lot better. The blue ones right here, okay, these are all the originals, and the gray colored ones, okay, those are all the ions then, okay, in there. So you can see that the ion is much smaller than the neutral atom. okay, in there. All right, the opposite will happen if you start having anions in there. So let's take oxygen. Oxygen is 8 protons, and that means 2 electrons here and 6 electrons in the second shell. And then 8 protons for the oxide. You have 8 protons and you still have the 2 electrons here, but now you have 8 electrons in the outermost shell. Okay? So now you have an imbalance again. So which one has a higher effective nuclear charge? The neutral atom or the oxide?
The neutral.
The neutral. Okay? Because again, this one is pulling on less electrons, but now here are more electrons to pull, so it's not able to keep up. Okay? The number of protons. And so you will see that the gray circles here are actually increased in size because now you have less effective nuclear charge. Okay, so let's make this a little bit better over here. So the cations, all the blue ones, okay, the blue ones are the neutral atom, and the gray ones here show you that you have the cation. The cation now, okay, there's also a trend over here because 1 electron versus giving out 2 electrons, okay? And remember we talked about something called isoelectric last time, and isoelectric was same number of electrons, okay? So for group number 1, it can give away 1 electron and become isoelectronic with the noble gas, okay? And then group number 7 will accept 1 electron and become isoelectronic with the noble gases. However, group number 6 is accepting 2 electrons to become this. Do you see the trend that I'm talking about? Okay, and so within the isoelectronic species, you can have a variety of sizes, okay, of the ions. And that's exactly what is shown here. So when you look at the trend for sodium, magnesium, and aluminum, look at the size of the cation going from large to small to even smaller, because these are all isoelectronic species now. Okay, so they have the same number of electrons but different number of protons, okay, in there. And the same thing happens, it's the reverse when you look at, we look at this one, this is a little bit larger. It is reversed when you look at the anions, because in anions, the larger number of electrons it receives, the larger the size gets, okay, because then the protons are not able to keep up, okay, so it's the reverse trend. So this is also something you will have to compare. The worksheet that I just gave you today has some examples in it, okay, for you to work on. Make sure you take this weekend and do all of that. And by the way, I did go on the homework today and no one has started 7 yet. Okay, maybe 1 or 2 of you have started 7, but please, 7 should be finished by now. Okay, so this weekend get on 7 and 8 and do them, okay, because once we go on to bonding, you know, we'll be getting on new stuff. So you master all of these things this weekend. Okay, so that's ionic radii, and that's also the trend that's given to you over here. Cations get smaller, okay, and the anions will get smaller as you go there, or increase as you go towards the left-hand side. However you want to write it out. And this essentially is all your periodic trends. Okay, and again, remember, periodic trends are only for the main group, not for the transition metals. Okay, nobody is going to ask you for transition metals. If they do, it's either a typo or they're tricking you, okay, because it doesn't happen. Any questions? Anything that's still bugging you? Oh, good. Okay. All right. In that case, here are some problems that you can go through. Bromine, selenium, tellurium. Okay, and this is atomic radii. Atomic radii. Okay, so when you see bromine, selenium, and tellurium, the first thing you do is, of course, look at the periodic table, right? Okay, so you look at the periodic table and you identify where all of these are. Okay, and you will get these a lot. Okay, you will get these a lot in the sense that you will either get 2 things in one row or things that are going down and above. So, you know, look at these 2, and between 34 and 35, selenium and bromine, which one is the larger atom? Atomic size decreases as you go to the right. Okay? No, not remembering the trends yet? No? It'll take a while? Okay, until next class maybe. Okay, so as you go towards the right, you should have the PowerPoints in front of you. As you go towards the right, the atomic size is decreasing. So then this is smaller, this is larger? Between these two, which one is larger? Tellurium or selenium? Tellurium. Okay, so what's the largest atom here then? Tellurium. Okay, so that's really how it is. Okay, it's a very simple kind of a thing. So that's how you would work. You know, take two things at a time and then work it out. Okay, in there. So bromine becomes the smallest atom then. Okay, amongst all of them. And this is how you will get it. It's very rare that you will get something that you cannot do. Okay, and if something like that happens, you can call me on it. Okay, that's fine. I will see if I made a mistake or is it something that you can really do. Okay, the same thing goes for ionization energy. You can work that out too. We talked about isoelectronic already. Okay, and this is how the atomic size changes. Okay, and the ionic size changes for isoelectronic species, so you can go over that too. But I already explained this to you. Okay, how it works. Anions will generally be larger than cations. That's absolutely for sure. Especially in the same group. Okay, the properties of the groups. Okay, now this one is really a very interesting part, and this is very much more interesting if you're in organic chemistry. Okay, and so you learn a lot about where these elements are found, how they exist, how they are extracted, how they exist. Okay, things like that. So there is a lot to do with you know, properties of all these elements. Jake, thank you very much. Okay, all right, let's pay attention right now. So there's a lot to do with how these elements exist, okay, in nature and what their properties are. It's very interesting, but I'm going to speed through this, okay, a little bit and just talk to you about some very specific things in there. The rest you can listen to the video online, okay, for the YouTube, because it's really actually quite interesting how these groups exist. But this is what I was just talking to you about, okay, over here with these reactions about metallic oxides and then the non-metallic oxide. So if you take any metallic oxide, add water to it, you will get a base. You take any non-metallic oxide and you add water to it and you will get acids. Okay, and there, and that generally is the case for all metals and non-metals. Amphoteric, this might be a new word, okay, that you're listening to today. And amphoteric actually means something that has both the properties of acids and bases. Okay, water is also an amphoteric substance. So amphoteric substances or amphoteric oxides will end up giving something that is amphoteric in nature, okay, which is both acidic and basic. These are the substances, if you look at this, aluminum, okay, which is in right here, it's also metalloids. Okay, so metalloids will tend to give you more amphoteric substance, which makes perfect sense because metalloids are also both metals and non-metals. Okay. Good. So you definitely have to know these properties, okay? So anyhow, go through that. Group 1, alkali metals. Really, I don't need to go too much over this, okay? Because there are just a few properties that I'd like to mention here. The rest you can listen on YouTube. So these are all metals. They all end in S1, okay? Of course, all the oxides are M2O, which is fine. That's what you would do with bonding. All the metals are very reactive, and of course, you know, we saw sodium yesterday. Well, Juan and I did. Okay, the rest of you, I'm sorry. But in any case, okay, they're all very, very reactive, and they're all very soft also, okay, which is not something that you expect, okay, from a metal. So they're really soft like butter, okay, you can just cut it through. So they're very interesting metals. So they have to be stored also very specially because they react very fast, okay. So you can look at lithium over here, look at the outside and look at the inside, okay, what a difference there is. And that's because of the reaction going on outside, okay, not because there is a peel to it, okay. There, you don't peel, you know, lithium to get lithium, no, nothing like that. It's not a banana. Okay, and then alkaline earth metals, which are group number 2. Group number 2 are also all metals. Okay, there's nothing about that. The interesting thing about group 2 is that they call earth metals because you do find them in the earth. Okay, a lot. So in a lot of soil, rocks, that's where you would find them. The oxides are MO. The reason the oxides are given to you, by the way, specifically is because we talked about this property of acids and bases. Okay, that's the only reason why that's given to you. Some of these will react to form hydrogen gas, and again we did that yesterday also, okay, with the magnesium. You take magnesium, react that with any acid, sulfuric acid or HCl, and you get nice reaction. That is also a way of testing, by the way, if you have a metal or not. Okay, so if you're not quite sure that you have a metal, you just throw in a little bit of acid, and if you get hydrogen gas, then you have a metal. Okay, non-metals will not do that. Okay, so that's what these are. Group number 3 is kind of now getting into metalloids. And so boron is a metalloid, aluminum gets into a little bit of metal properties, and then aluminum will react with acids and bases also a little bit. Okay, and then that's kind of what, there is not much to tell in here. You don't even encounter a lot of these metals over here. Gallium, the only reason we talk about gallium in a GenChem class is because it has such a low melting point that you can take it in your hand, it will melt, which means that your body temperature is enough to melt it. Okay, that's how low the melting point is. You know that in the entire periodic table, there's only one metal that's a liquid, right? And that's mercury, exactly. So most of the metals will be solids. That's how you recognize metals. So it's very rare that you find any metal that has such a low melting point. Okay, most of the metals have very high melting points, which is why they're good. They're stable at high temperatures. Okay, group number 4, really, really interesting. I think group number 4 is one of my favorite groups because it has everything in it. Okay, and now all the elements that you see in group number 4 are useful one way or another. If there was no carbon, there would be no us. Okay, because we're all carbon-based forms. And carbon is also a non-metal. Okay, silicon and germanium, those are two getting into metalloids. Okay, with this, and then tin and lead, those are metals. Okay, very traditional. So really nice, very nice group. And of course, being an organic chemist, I really have an affinity to carbon in general. Carbon is also very interesting, okay, because carbon exists in different forms, okay, and yesterday in my lab when I was asking about where you find carbon, the first thing that came to everybody's minds was, not everybody's, some people's mind was diamonds, and I was very impressed actually by that because people don't think of diamonds as carbon, okay, people think of diamonds only as precious stones, exactly. You know, so nobody thinks of it as carbon, but really it is carbon. Okay, and only carbon. If you find any colored diamonds anywhere, like the Big Panther, okay, or something like that, that actually has some minerals in it. Okay, so it had additional things in it which give it the color, which also makes them even more precious. Okay, because and it's just a way of making elements. And I love talking about the carbon because it is very interesting. Carbon also exists as something else, anybody? Coal. So you have coal, we have diamond, what else do we have?
Yeah. Carbon is gas.
Got gas? Okay.
Carbon's not a gas.
No.
What am I talking about?
Anybody else?
Graphite.
As graphite. So you have these forms, okay, of carbon, and specifically I want to talk just a little bit about diamond and graphite because those are two very, very different, okay, kind of substances. Have you ever thought about writing with a diamond? No, but graphite you write with all the time, right? That's what you have in your pencil. Okay, that's what's called the lead, okay, in the pencil, that's graphite. So every time you write, you leave a layer of graphite, okay, on your paper. That's what's going on, okay? But you never would do that with diamond. On the other hand, you also know diamond is one of the hardest elements out there, right? Only a diamond can cut a diamond, okay, as we know. So now lasers can too, okay, but otherwise only a diamond could cut a diamond. So it's a very, very hard substance. So the question is, next question, where do you find diamond? In the earth, where? Like on the surface, under the earth, you know, you have to mine for it. What do you have to do? In caves? Good. Anything more? Diamonds you generally find underground. Okay, you will never find them on the surface because it takes forever to form a diamond, and that's why diamonds are precious stones. Okay, they're not invaluable for nothing. Well, part of it is of course zeals and whatnot, trying to make it more precious for you. Okay, that's the whole selling tactic. Otherwise, it's just a rock. Okay, that's all it is. But still, nobody proposed to their girlfriend with a graphite. You know, here this is carbon too, right? But it's not the same thing, right? So it's a different thing, okay? And so it takes a really long time to make a diamond because it has to be under pressure, okay, for a long time. So you keep it under pressure, and that's how it hardens and it hardens. And it is so hard then that only a diamond can get a diamond, okay? And then graphite, on the other hand, where do you think you'll find it? On the surface or underground? Probably on the surface, okay? Because it doesn't have to be hard at all, okay? And so coal mining also, which is done a little bit underground, it's not so much because it is found only in underground. You can find coal outside also, okay? But underground, of course, there is more of it, okay? And so it depends on the nature of the substance. So which means that there has something to do with the structure of diamond and graphite that is very different, okay? And those kind of substances are called allotropes. You may hear of this again in GenChem 2, maybe you will not, okay? It depends, some teachers cover it, a lot of them don't, okay? Because this is not something that you really encounter a whole lot, but allotropes are the same element with just a different structure, okay, to it. Another example of an allotrope, just so that for your point of reference, you know, it's oxygen and ozone, okay? Because these are also the same element, but they exist slightly differently, okay? So they're called allotropes as well. Diamond and graphite are different because carbon is more C4 based and graphite is more C6 based, okay? Which means that by the time you get the molecular network of all the atoms that are joined together, atoms in solid structures are not just random, they're not random, okay? They're very, very systematically made, okay, in a very, very organized manner. So the diamond, okay, it's more like chicken feet, like this, where you have everything coming out, and that's why it's called a C4 structure. And you can see it's highly, highly compressed because it's very close to each other, okay? That's why it's so hard. Graphite, on the other hand, is based on hexagons because it is a C6 structure. So it's kind of like this. And when you have something like this in hexagons, you can see that it will be easy for it to kind of slide out, okay, from one on the other to the other. Whereas diamonds is not able to do that, okay? And that's why diamond is cut very nicely, okay? You can do that and you get these very nice cuts and shapes for diamonds, and it'll look, you know, it'll look pretty, okay? But you can try with graphite, it's never going to look that way, okay? Because it's just different, all right? And you may have heard of artificial diamonds also. Yes? Okay, yeah. So you can actually make artificial diamonds by taking and just, you know, compressing them artificially. And since they're all carbon-based, you may have also heard, don't know, that people whose pets and loved ones die, they get diamonds made out of them. Have you heard of those? Precious stones? No? And then you wear them, you know? Yeah. Okay. You haven't, that's fine. But it started a few years ago, you know, when you could, because everything is just carbon. It's just atomic, okay? Yeah. We like to give each other some personality or something, but essentially we're all carbon-based atoms. But in any case, that's carbon, and there's one more allotrope of carbon. I will let you explore that and come back to me on Thursday and tell me, okay? Because today is not Thursday, as I was told. So come back on Thursday and tell me the third allotrope of carbon, okay? And I promise you I will give you chocolate. I do have chocolate, okay? I will bring that, and anybody who tells me the third allotrope of carbon. Okay, so then we have all of these, and then tin, okay, and lead, which are at the bottom. Those are what we also call heavy metals in some ways, and they're also metals, okay, very truly metals. Okay, group number 5, okay, now we're getting more into non-metals, and there's only one metal, okay. Bismuth is probably the only true metal in there, antimony sort of, okay, and then arsenic is definitely not, okay, and arsenic you may have heard of as the common poison, right? Yeah. Arsenic and Old Lace, have you seen that movie? Hilarious movie, okay, very old movie of course, but still. In any case, okay, nitrogen is all up around us, okay, very, very useful element, okay, not just that it exists in air, but you find nitrogen also in fertilizers and whatnot, okay, so the plants need it all the time. Right? So, of course, the problem with nitrogen is that nitrogen can also be explosive. Do you remember we were doing a problem back when for gases when we talked about sodium azide, NaN3, which is then found in, yeah, we make airbags out of that. So it's very explosive. So a lot of nitrogen compounds are very explosive. That's one of the bad parts. Phosphorus, which is right under nitrogen, okay, is pretty common also. Phosphorus is also used in fertilizers, okay, and all that. So anyhow, that's group number 5, not so much there. Group number 6, we don't talk about it much. If you think about, why we have so many elements and what do we do with these elements, it's really very interesting, okay? And it's something that you have to explore on your own, okay? It's not so much time that I have. If you go to my YouTube channel, there's one that I have subscribed to on there. It's called the periodic table videos, okay? If you have 5 times to kill somewhere, you're sitting at a traffic light or whatever, I don't know, and you just want to kill 2-3 minutes, go to those YouTube videos and look at an element, okay, from there. Anything that you're curious about, okay, and find out what do we do with whatever, okay, pick your pick, okay, and then go through it, okay, because even I don't know, okay, what they do with all of these, but it's very interesting. So oxygen we breathe, nobody can live without oxygen, and of course sulfur, very common as well. I did not even think about this, but yesterday one of my students mentioned in the lab, when we were talking about this, is of course we find sulfur in a lot of volcanic areas. Okay, and I don't know if you've ever gone to Hawaii, to the Volcanic National Park. If you walk there, you'll just see sulfur deposits right there. Okay, it's all there. So it does come out of the earth and it is very stable. It's a solid versus oxygen, which is a gas. Okay, so by the time we come down to sulfur and all the others, they are solids now. Okay, and by the way, I forgot to mention, of course, I was going so fast, nitrogen is a gas as well, right? Okay, we did talk about that. So nitrogen is a gas, which means we are now changing our phase also in which we occur. Okay, so as you can see yourself, and getting into halogens now. Iodine you have seen already in your lab, okay, because you did the beautiful sublimation where you had the very lovely purple colors, okay, in the lab. So you've seen iodine before. Fluorine nobody gets to see because fluorine is a very reactive gas and it's just a gas, colorless. Chlorine, on the other hand, you might see it or not see it, but at least smell it. Okay, if you ever jump in a pool, you will smell chlorine gas. Okay, and that is the disinfectant. Or you just have to open a bottle of Clorox. Don't stick your nose into anything. Now you know better. Okay, but if you take a whiff of it, that is chlorine. Okay, in there. Bromine is a liquid like this. There are 2 liquids on the periodic table: mercury and bromine. Okay, the rest of them are either solids or gases. And bromine also very toxic substance. Okay, and you can see the gas here, and to breathe that is even worse. Do you remember your copper reaction you did and you got the nitrogen dioxide gas, the brown colored gas? This is the same kind and it's also awful. Okay, and so it's just not very good to breathe in. Iodine is a little bit less toxic because it's solid. Okay, but other than that, it's also very toxic by itself. Okay, and then of course group number 8, we get to noble gases, which are truly noble. Please leave me alone, don't touch me. Okay, and so these are very different. Okay, all the valence shells are filled, and we remember the magic number. Valence shells can have number of electrons? 8. Okay, always. This will come really handy in the next chapter. And typically they will not react with anything. Okay, most of them are called inert. But later the compounds were formed, and you will learn that in the next chapter, how the compounds were formed for some of the noble gases. They're still not easy to react, okay, but they can react. But otherwise, really not much to it, okay? Although I know that if the helium reserves were depleted, you would have issues with them, right? That would be tough, okay? But anyhow, that is the periodic table for you in a nutshell, in like 5 minutes, I think. And that's about it. Do you have any curiosity questions or any general questions about the periodic table? No?